Dear students, we are going to look at the first law of thermodynamics applied to the open systems today. After attending today's lecture, you will be able to attempt simple questions like this, which have been asked in GATE. Let us quickly go through what exactly we will do in this lecture. We will learn different types of open systems. We'll learn what is conservation of mass for open systems. We'll relook at flow once we have done it, but we'll relook at it. We will understand how to derive the steady flow energy equation and then how to apply the steady flow energy equation to nozzles and diffusers, turbines and compressors, throttling devices, and mixing chamber. Basically, the steady flow energy equation is the first law for open system. Let us start. So these are some of the examples of open systems in engineering, specifically with respect to aerospace engineering. So you have nozzle, which changes the enthalpy of the fluid to increase the velocity. Then we have turbine, which produces work, and we have compressors, which consumes work to increase the pressure of the fluid. We will understand this in much detail later on, but for today, we will try to apply the first law of thermodynamics to this open systems. Now, open system is also referred to as control volume. Now, suppose, for example, let us consider this turbine. So we take up the turbine, right? And we consider it to be our open system, which is also referred to as control volume. And why it is referred to as control volume? Because generally, open system does not do any displacement work. The volume remains constant mostly, right? So we study the volume of this system and what exactly is how is it interacting with others, right? And in an open system, right, both mass and energy are permitted to enter and cross the boundary. So mass can come inside, right? And mass can go out, sorry, OUT out. Energy can come in and energy can go out. So this is what is open system, right? Now, first look at the conservation of mass principle. Whenever as I have told, right, in an open system, the mass can come in and mass can go out. So what conservation of mass principles tells is that the change, the mass going out minus mass coming in is equal to, or you can also say it vice versa, change in mass of the control volume. Now, generally, we will see 99% of the times in these flow devices, the change in mass is going to remain to 0. If that is the case, what you can say by conservation of mass, sorry, by conservation of mass coming in is equal to mass going out. So this is basically conservation of mass principle. This can be applied to nozzles, turbines, compressors, throttling devices, mixing chambers. But there are also certain open systems where does not hold true. For example, charging of a tank, discharging of a tank. We can have a look at it separately, but in today's class, whatever you are going to study, especially which will be applicable for all the aerospace engineers, the mass coming in shall be equal to the mass going out. Now let us see what is the critical difference between open system and closed system. Now we have discussed this earlier, but I would like to discuss this once again because this is very important and this is what defines the enthalpy. Now, as I said, the mass is going in to the inside the control volume. Let me define the control volume. Let me say this is the control volume, right? This is the control volume, our open system, which we are going to study. So basically, this is a converging diverging nozzle. We'll learn about it properly later on. Now, suppose this is the amount of mass that is about to get in. So we have certain mass here, mass of fluid, which wants to get into the nozzle. So this is mass going in. Now, you see the control volume is already full with particles, right? It already contains certain mass. So for this piece of mass to get inside, it has to be pushed inside. It cannot simply go. It is not empty. The control volume is not empty, so it cannot simply go. It is full. It also has some pressure. So it has to be pushed to get inside. Now, who is going to push this mass element? Definitely the fluid which is behind this fluid is going to push it. Now, when it pushes, some amount of work has been done. Some amount of work will be done on this fluid, and that work stays with the fluid and it is known as flow work. And it is known as flow work. So let us quickly try to see what is flow work. Let us quickly try to see what is flow work. Right. So let us assume this is the element of fluid that is getting inside. We are applying a force F. Right? Let me assume that the fluid behind the element which is going inside, let me say it is assumed to be an imaginary piston. And this is the fluid element going inside whose length is L, the area of cross section is A. So what is the net work done? What is the work done on the fluid? Work done. Work done can be represented as force multiplied by displacement, which is L. Now force is equal to pressure into area. So it becomes PAL. Now if we combine the area and volume term, the length term, so it is nothing else but PV. Right? So you see the work done is also can be also be written as PV, and this is nothing else but this is known as the flow work. So this is the amount of work that was required to be done on this fluid element for it to flow inside the control volume. And this amount of work stays with the fluid element, right? And it moves with the fluid element. So if you want to see what is the total energy of a flowing fluid, the total energy, let me say, for stationary fluid, for stationary fluid, we know what is the energy. For stationary fluid, we can write it as internal energy, right? Let us write it in per mass basis, right? The specific property, specific internal energy, in fact, right? We've spoken about it, small u, plus we'll have kinetic energy, right? And we'll have potential energy. This is the, I'll also make E smaller, right? So that it represents energy per mass basis. Now, once the fluid starts moving, it has an additional energy for moving fluid or flowing fluid. We can write, let me say, we write it as theta. So this is equal to U. This you will have already this energy will be there, but along with it, we have another form of energy that is P into V. It's just P into V. Now, if you combine, we can rearrange it a little bit. Let me say this is U plus PV plus kinetic energy. I can write it as V square by 2, mv square by 2, but this is written per mass basis, right? mgz, but I'll write it as gz because we're writing it in per mass basis, right? So U plus PV, it can be combined, and this is the combination property which we have seen even earlier, which is known as enthalpy. H plus V square by 2 plus Gz. So what I'm saying is per unit basis means all the energies are written kilojoule, has to be written in kilojoule per kg. Kilojoule per kg, right? So you have to multiply mass to get the total energy of the flowing fluid. So let us see what is the energy transported by mass. So the total energy which is being transported can be written as mass multiplied by enthalpy plus V square by 2 plus G Z. Right? Now let us try to understand what is steady flow. Right? It is very important to understand steady flow. The first law of thermodynamics for open system is known as steady flow energy equation. So understanding the term steady flow becomes very, very important. So what is steady flow? I'll just give you a quick description of steady flow. Steady, what is the meaning of steady? Steady means things which are not changing with time. So if we have a control volume like this, right? So the change in mass of the control volume, with time is going to be 0. So the control volume, the mass is not going to change. Change in energy of the control volume is also going to be 0. And the properties at the inlet and exit will remain same. So the properties at the inlet and exit is not going to change. If the mass flow rate at inlet is m1 and enthalpy is h1, is not going to change with time. So if you see this is a two exit case. So if you conserve the mass, so I can write it as m1 is equal to m2 plus m3, and h1 should be is equal to h2 plus h3. That is not the case, we know. The energy, if I'm talking about energy, it is not just the enthalpy, it is also kinetic and um, potential energy. If this change in kinetic and potential energy is 0, then we can write it this way. We'll see this. Okay, we're going to see this in some time. So this is the meaning of steady flow, the properties, right? The properties at the inlet and exit does not change with time. Total mass or energy entering the control volume must be equal to the total mass or energy leaving it. Okay. Having said that, let us try to understand energy analysis of a steady flow. It's quite simple. If you've understood the things till now, it's going to be quite simple. Now let me consider a turbine. So this is how the turbine is being drawn. Right? So let me consider a turbine, and let me say certain amount of fluid is flowing in and then certain fluid is flowing out. The enthalpy of the fluid, this is the inlet, right? I N L E T, inlet. Let me mark inlet as 1, and this is the exit, right? Let me mark exit as 2. So the properties at the inlet are the enthalpy is H1, the velocity is V1, the height is H1. Properties at the exit are enthalpy is equal to H2, velocity is equal to V2, and the height, the elevation from the ground, let me say it is Z2. No, this is Z1 is going to be equal to Z2 most of the times, but still, right? Let us try to understand it is in a general flow because turbine is a specific kind of entity. We are trying to write the general equation, general analysis. Now let me say the mass flow rate. If you talk about the mass flow rate, whatever mass is coming inside, the same amount of mass would be actually going out in this case. So if you want to write the energy equation, so total energy entering, right? Total energy entering the inlet, right, is equal to mass into H1 plus V1 square by 2. This is the kinetic energy part plus GZ1. This would be is equal to M. I'm writing it as M, right? Because we all know M1 is equal to M2, right? It is equal to H2 plus V2 square divided by 2 plus G Z2, right? So this is not complete. This is not a steady flow energy equation. This is just energy analysis of a steady flow. So you can see the total energy coming in. Okay, I can write total energy which is coming in is equal to total energy going out. Now there are one more point to this. Let us see what is that point, right? The turbine can also do some work and there might be also some heat transfer to the turbine. Let us now add the heat and work term and form the complete steady flow energy equation. So this is basically the first law for open systems. So let us consider a turbine. Right? It can be any open system, it need not be a turbine. If you want, I can also consider a nozzle, right? Whatever it is, right? It can be any kind of open system. So this is the inlet. Let me mark the inlet as 1. This is the exit, which is S2. So the properties at inlet are H1, V1, G1, and at exit is H2, V2, G2, right? And some amount of heat is being transferred into the system, right? And some amount of work is being done by the system. So soft work, generally the kind of work that the turbine is going to do is soft work. So work is being done by the system. So we had written the steady flow energy equation, right? Let us rewrite what we have written it in the last slide. So you can say total mass flow M H1 plus V1 square by 2 plus, we can make it M1 if you want. Okay, we know M1 is equal to M2, but let us write it in a generalized form so that we can apply it for any kind of systems, even if we are doing charging, discharging. H1 plus V1 square by 2 plus G Z1, right, is equal to, this was the inner equation which was, we have seen it in last slide, H2 plus V2 square by 2 plus G Z2. Right? Now here we are going to add two terms. Try to see this. First, we are going to add the heat term on the left-hand side. Heat is being supplied, right? And work is being done by the system. We are writing it on the left-hand side. So now this equation becomes the complete energy flow, steady flow energy equation, SFW. Now you have to keep it in mind that these terms are specific, means generally they are written in kilojoule per kg, whereas this is not specific, this is written as kilojoule. So the units, the one of the points where most of the students make mistake here is not writing down the equation, but not understanding the units properly. For example, in all the equations, H1 will be given in kilojoule per kg. But if you calculate V1 square by 2, the amount of energy that will get will be in joule. So we'll have to convert it into kilojoule first. Right? We'll see this while doing the problem. Now let us try to apply this steady flow energy equation to some of the common engineering devices. Generally, these are the devices that we are going to see. So let us apply this to nozzles and diffusers first, right? And before that, let us try to understand what is nozzles and diffusers. Well, we will study nozzles and diffusers, be turbine compressors in much detail later on. But for now, just let us introduce these devices to you. So nozzle is a device which increases velocity at the expense of pressure, we can say. And pressure is nothing else but, you know, it is a enthalpy. Pressure is, what is enthalpy? PV, U plus PV, right? So pressure decreases means also I can say enthalpy decreases. So you can say increases the velocity of the fluid at the expense of pressure or enthalpy. Right? And diffuser is simply the opposite of it. It increases the pressure, right, by slowing down a fluid, means velocity is converted into pressure. And these devices are very, very important for any engineering, especially in the aerospace industry. Now let us try to apply the steady flow energy equation for a nozzle or a diffuser. So the nozzles, they are generally drawn this way, right? Diffusers are drawn this way. Sorry. Diffusers are drawn this way. right? So this is the inlet, this is the exit, this is the inlet, this is the exit, right? So mass is coming in, mass is going out, mass is coming in, mass is going out. So if we want to write down the steady flow energy equation, simply it is going to be m1 h1 plus v1 square by 2 plus g z1 plus q is equal to m2 h2 plus v2 square by 2 plus g z2 plus w. Now, let us try to understand few things. First of all, the nozzles and diffusers will be assumed to be what? They assume to be insulated, means the process is going to be adiabatic. So once the process is adiabatic, so the heat transfer is going to be zero. And nozzles and diffusers are not work producing device, so they will not produce or consume any work. So this is also going to be zero. Assuming the elevation to be same, and now assuming that the mass flow rates are same, so we can also cancel the mass flow rates. Assuming that there is no change in the height, right? Because they are kept horizontal, these parameters will also get cancelled out. So once you cancel out all these terms, what will be left out with simply h1 plus v1 square divided by 2 is equal to h2 plus v2 square divided by 2. So the steady flow energy equation for a nozzle reduces to this. Let us try to attempt a problem and understand this equation even more. So you can see in this question, steam at an initial velocity, enthalpy, 100 kilojoule per kg. So whenever we are attempting a problem, let us draw the diagram and insulated horizontal nozzle, right? So this is the inlet. So what are the properties? H1 is equal to 100. You can see the unit is kilojoule per kg, right? Specific properties given. And initial velocity V1 is equal to 100 meter per second. And at the exit, H2 is not given. We need to find out what is the exit enthalpy. However, the velocity V2 is given to be 200 meter per second. Now, it's a insulated horizontal nozzle. What is the meaning of insulated? Insulated means definitely it is given that there is no heat transfer. So this is not a hard and fast rule, but generally this is how it will be, right? And we all know that the work transfer is equal to zero, right? Nozzle is not a work producing or work consuming device, right? And it is also horizontal. What is the meaning of horizontal? What it means that Z1 is equal to Z2. So you see the equations, whatever we cancelled out, all the equation in the equations last class, we can write down the full equation first and then start cancelling out and arrive at this point. So M1 is equal to H1. This is the full equation, but we need not write the full equation each and every time. H1 plus V1 square by 2 plus G Z1 plus Q is equal to M2 plus H2 plus V2 square by 2 plus G Z2 plus W. So you can see it is insulated, so it is zero. It is not a work producing device, it is zero. Elevation is, it is horizontal, so this is also going to become zero. And since it is a steady flow device, now we can cancel up the mass also, M1, M2. So the equation reduces to H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. Right? Now, what are the parameters given? H1 is given to be 100. Now, look at this very carefully. 100. Velocity is V1. V1 is 100 square divided by 2. Now, if you calculate this V1 squared, if you write down the units, what is the unit of V1? Unit of V1 is going to be meter per second. Meter per second into means meter per second square. So, it is going to be meter into meter per second square. Definitely kg will be there, right? Because if you once you and multiply the mass. Now, if you look at this carefully, if you look at this unit carefully, right? So this is actually kg meter per second square. If you combine this kg meter per second square, this is going to be force. Meter is the displacement. So force into displacement is joule. So this unit is in joule. So you have to convert it into kilojoule. So you will have to multiply by 1000. So this conversion is very, very important. This conversion is very, very important. We'll have to practice some more question on this. We need to find out what is H2 plus V2 is given 200 whole square divided by 2. Again, you'll have to multiply by 1000. Why? Because 100, you see, it is given in kilojoule per kg. Right? So you make sure that you take care of this units from here. If you calculate, you'll get the value of H2 as 85 kilojoule per kg. Right? It wasn't very hard. Now let us look at turbines and compressors. The turbines and compressors, they are work producing and work consuming devices respectively. Now, what do I mean by work producing device? For example, in a turbine, the enthalpy of the flowing fluid is reduced, and whatever decrease in the enthalpy, right, it is converted into work, soft work. So some amount of work will be produced, and this work is generally used to drive, say, compressors, to drive many other parts. We'll go into much detail with respect to turbines, water turbines, right? But for the time being, let us try to understand that turbines are work producing device. There will be a drop in enthalpy, and as a result, there will be some amount of work being produced by the turbine. Similarly, if you take the category of compressors, the pumps, compressors, and fans are kind of in the same category, right? Pumps are basically mostly for liquids. Compressors, mostly we use it for gases. But ultimately, the work of both of them are similar, and it is quite similar to that of fans. So these are work consuming. Why I am saying work consuming? Because we have to supply work to the compressor from outside, right? So, and what the compressor is going to do, it is going to increase the pressure. Basically, it is going to increase the enthalpy, and as we know, enthalpy is equal to internal energy plus PV. So it is basically what is going to do, it is going to increase the pressure component. This is what it is focused on. It is increasing the pressure component. Yes, some amount of internal energy also increases because of the work done on the gases, which will also result in increase in temperature, right? But mostly what is the main point of compressor is to increase the pressure. We'll see it in much detail, but for now, let us try to apply the steady flow energy equation to a compressor or a turbine. Now, the turbines are drawn this way because the fluid expands, and compressors are drawn in just the opposite manner because the fluid contracts from inlet to outlet, right? So this is one, this is inlet, this is a turbine, and this is the outlet, which I'm representing as 2. And this is the inlet here, right? And this is the outlet here, which I'm representing as 2. This is 1, let me say. Now you see this simply drawn, the diagrams are simply opposite to each other. From turbines are from decreasing cross section to increasing cross section, whereas compressors are from bigger cross section to smaller cross section. So the basic difference is because in turbine the gases get expanded, in compressor the gases get compressed. Right? Now, both the turbines and compressors are work producing, work consuming device, but one thing is for sure that we are going to consider them to be insulated, means will not allow any heat transfer. This is a basic assumption. It need not be so. In higher level problems, you'll see we'll just cut off this assumption. Let us write down the steady flow energy equation, a general steady flow energy equation. So I can write it at mass flowing in H1 plus V1 square by 2 plus G Z1 plus Q is equal to mass flowing out, which is also equal to the mass flowing in, H2 plus V2 square by 2 plus G Z2 plus W. Now, the first thing we have to note that the heat transfer is going to be zero because we have made it insulated, right? Be the turbine, be the compressor. So we'll consider the heat transfer to be zero. Now, if you see, both of them mostly, because these are not very big devices, so most of them, most of the time, they will be horizontal, or the change in Z will be almost negligible. We can cancel this too, right? Well, there might be velocity change. Yes, there might be velocity change. There might not be general velocity change. And let me write down the assumption for you if you want, right? So generally, right, or normally, right, change in kinetic energy is equal to change in potential energy, right, is equal to zero. So if that is the case, we can actually cancel this two also, right? And because it is adiabatic, insulated, definitely Q is equal to zero. So now if you see, the equation reduces to something like this: M1 H1 plus Q, okay, Q is equal to zero, is equal to M2 H2 plus work done, right? So M1 H1 will become capital H1, capital H, these are not specific property, plus W. So, or what you can write it down as, or simply you can write it down as that the work done is equal to mass into change in the specific enthalpy of the fluid. So this equation remains valid for both compressors and turbines. The only difference that is going to be is that in compressors, H2 will be greater than H1. So work done will come out to be negative. In turbines, H2 will be smaller than H1 and work done will come out to be positive. And that's it. So it's quite simple. Now let us try to attempt a question which was asked in GATE Mechanical 2001 for 1 mark. Now, if you see, compare mechanical and aerospace also, steady flow energy equations are very important because all our systems, thermodynamic system, most of the thermodynamic systems we'll be using are open systems, right? But basic level questions are not being asked the way it is for mechanical engineering. So you will always get a question level above. So we'll be able to attempt those questions, right, which are asked in GATE Aerospace only after learning these basics, and that is one of the reason why I'm conducting these classes very fast, right? So that we can quickly move on to those sections which are very important for aerospace engineers, and they will be able to solve the actual problems which have been asked in GATE Aerospace, right? So we are moving a little bit fast out here so that we can give more time out there. A steam turbine, okay, receives steam at 10 bar with an enthalpy of 3000 kilojoule per kg. So I'll draw the turbine, which helps me visualize the things properly. And I suggest all of you to draw a diagram, which will always help you to visualize the things properly. And if you are able to visualize correctly, then the probability of you answering it correctly also increases. So what is the pressure one? Pressure at terminal 1 is given as 10 bar, okay? And the enthalpy is given as 3000 kilojoule, right? H1 is given as 3000. The units are very important, kilojoule per kg, right? And it discharges. This is the inlet, which is 1, and this is the exit, which is 2. So it discharges with an entire pressure P2. You can see the pressure has dropped, and as a result, I'm sorry, uh, this is not the pressure, this is the enthalpy. So pressure is 1, but you can see the pressure has dropped, and as a result, you can see there has been also a drop in the enthalpy, right? And it is saying that the work output is equal to 250 kilojoules. So it is producing some amount of work. Turbine is producing some amount of work that is equal to 250. Again, it is given in kilojoule per kg. This is very important, right? So let us try to write down the equation, right? For and even before that, The changes in kinetic energy and potential energies are negligible. So delta KE it is given in the equation. Delta KE is equal to delta potential energy, which is equal to 0. But here, one thing if you notice, right, the turbines, the heat transfer from the turbine casing to the surrounding is equal to. So heat transfer is being asked, right? So unlike in the last equation, here the heat transfer is not going to be 0. So let us quickly write down the full steady flow energy equation. Mass flow rate at inlet H1 plus V1 square by 2 plus G Z1 plus the heat transferred is equal to mass at the exit H2 plus V2 square by 2 plus GZ2 plus work done, right? Now some of the things will get cancelled out. What you can see, the kinetic energy, change in kinetic energy and potential energy are same, so I'm cancelling it out, right? Let me consider the unit mass, right? If I'm considering unit mass, so I can write down this equation as H1 plus Q, because both of them, Q, even the work done is given in unit mass basis, is equal to M2 mass. Okay, I did not write mass because I'm considering mass to be 1, right? Let M is equal to 1 kg. So I'm writing it for unit mass basis. H1 plus Q is equal to H2 plus W. Now some of the values are given. Let us substitute those values. What is H1? H1 is given as 3000. Again, see the unit, 3000 kilojoule per kg, right? Plus Q is equal to H2 is 2700 kilojoule per kg, right? Plus work done is given as, that is the work done by the system, so I'm considering it to be positive 250. So from here, if you calculate what is the value of Q, Q will come out to be minus 50. So Q will come out to be minus 50 kilojoule per kg. So what is the meaning of minus 50, guys? The minus 50 means simply the heat is being lost by the turbine. So heat is flowing out of the turbine, right? And you can see in the question, the heat transferred from turbine casing to the surrounding is being asked. So I can comfortably mark heat transferred from turbine casing to the surrounding is 50 kilojoule. And the answer is also given in per unit mass basis. I hope this is clear to all of you. Now let us move on to, now let us look at the example of throttling device. The picture that you can see on the screen is nothing else but you can consider it to be a throttling device so that you can understand throttling devices properly. Now all of you must have seen these spray bottles. Now there is a condition when we rotate this cap, right, and we achieve a condition where what happens is that when you spray, right? The spray, it sprays like all particles, small particles in all direction, right? So that kind of spray is being achieved. And that is an example, you can say, that is an example of what throttling does, right? So the water flows up through the pipe because of pressure difference, and then it is made to pass through a very small passage. And what happens when it passes through small passages? That is, it spreads. And exactly the same thing is done in our deos, right? This is how we spray. The fluid, the gas is allowed to pass through a very restricted small passage, and because of which there is immense amount of pressure drop. So this is the example that I just now took is the example to understand what is exactly throttling process. Now, throttling, as I said, is a process, kind of process, where the flow restricting device is used. So we use a flow restricting device. It could be a valve, it could be a porous plug, or it could be a very long capillary tube, right, which causes a significant pressure drop in the fluid. Now, what happens is that pressure and temperature are proportional to each other. We have seen they are not independent of each other. Now, if pressure drops, what happens? The temperature also drops. And because of this, right, the throttling devices are very commonly used in refrigeration and air conditioning applications. So even if you have an air conditioning system in the aircraft, we need the throttling device. So let us see what exactly happens inside a throttling device. So you can see the internal energy because of the temperature. We all know the internal energy is a function of temperature. Now, because the temperature decreases, the internal energy decreases to some extent, not much, but to some extent. Now, here the pressure drops immensely, but at the same time, it is accompanied by a extensive increase in volume. Just imagine when you spray a deo, right? All the gas is contained inside that bottle, and when it is sprayed out, the amount of volume it occupies is immensely large. And as a result, what happens? The volume increases. So overall, the multiplication P to V2, the flow work, it increases dramatically. So now, if you look at enthalpy, will be summation of internal energy and flow work, right? This remains constant. Even though there is a pressure drop, there is a temperature drop, but because of substantial increase in volume, the enthalpy remains constant. And that is why we consider throttling process to be an isenthalpic process. Right? We consider throttling to be an isenthalpic process. We call it, and it simply means that the enthalpy remains constant in the inlet and the exit. So what will be the, it's very simple for a throttling device. We don't need to write anything else. If, right, there will be no change in kinetic energy, right? Considering that kinetic energy change equal to 0, potential energy change equal to 0, right? And there is no heat transfer, right? So I'll make it 0, right? Throttling devices are not work consuming or work producing device, so work is equal to 0. So if we apply all these equations, you can simply write H1 is equal to H2 for a throttling device. It is called isenthalpic process. Now let us look at the final example of open system where which is important is mixing chambers. Now mixing chamber, I'll just simply give you an idea of a practical mixing chamber which we encounter in our day-to-day life. Now you've seen these showers, right? One is the hot, one is the cold. Now suppose you want a certain amount of water at a certain temperature. What we do, we adjust, we open it both hot and cold, and we adjust it accordingly, right? So that we get the right temperature at the outlet, be it the shower or be it the tap. So what happens? Hot water comes in and the cold water comes in from different direction, and they get mixed up here. Somewhere here they get mixed up, right? So this can be called to be the mixing chamber. So where you are mixing the both hot and cold fluid, right? The section where the mixing process takes place is referred to as mixing chamber, right? So how can you write down the equation? It's quite simple. We can write mass of hot, enthalpy of hot fluid is being mixed with what? The mass of cold into enthalpy of the cold fluid. This should be is equal to mass of hot plus mass of cold. This is the total amount of mass that is coming out, right? Multiplied by final enthalpy. So this one equation represents the, we can say that energy balance equation for mixing chambers. So that's all for today. The next lecture will be on second law of thermodynamics. Hope to see you there. Guys, I'll request if you are going through this video, let me know what are the things that you're liking about this video and what are the things you really want me to improve so that I can be of more help to all of you. And at the same time, I'll be uploading all the notes, all the question papers, question banks, so that you can practice for GATE aerospace paper through this channel. See you. Bye bye. Take care. Thank you, all of you.